podcast is brought to you by LMU Munich.
Okay, thanks. It's a pleasure to be here. Thanks for the invitation to this conference. And I thank the organizers for organizing a wonderful conference. And they are striving that everything goes very well. They even corrected some typos that were in my transparencies when I sent them yesterday. So they are really working very hard. This is work I've done with my student, Alexander Chiboyedo, and the motivation is the following. So we know that elementary particles can have spin, and even massless particles can have spin. But interactions of massless particles with spin are very highly constrained. So for example, for spin 1, we get Yang-Mills theory. For spin 2, we get gravity. And for spin bigger than 2, we don't seem to have an interacting theory in asymptotically flat space, as we expect from the Coleman-Mandula theorem that the flat space S matrix cannot have extra symmetries beyond the super Poincare group. Of course, for this argument, we need an S matrix, and we were surprised by the argument, the theory of Vasiliev, saying that in ADS we can indeed construct interacting higher spin theories, and that is consistent because these theories don't have an S matrix, and also they involve an infinite number of higher spin fields. Now, this result is best understood by thinking that ADS4 is dual to a three-dimensional conformal field theory, and then massless fields with spin bigger than 1 in ADS are dual to conserved currents of spin S on the boundary. And so the idea is that there's a conjecture dual to this Vasiliev theory, which consists of n free fields in the singlet sector, where the currents are constructed as bilinear operators in terms of these fields. And these operators correspond to the massless fields with spin in the bulk. So on the boundary, we have a free large n theory. And when we insert operators, we create a pair of particles and we contract them. The particles on the boundary are free. In particular, you will get a non-trivial three-point function by contracting the operators in this way. And that implies that the theory in the bulk should be also interacting, because the bulk interpretation of this is the fact that you created a particle here dual to a massless high-spin field in the bulk, and this three-point function has to be non-zero because it was non-zero on the boundary. So this picture gives you an explanation for, in some sense, for why this Vasiliev theory had to exist. Okay? And also, if you had n fields, you get that the Newton constant would be proportional to 1 over n. And all this was reviewed in C in stock. Now, one question we can ask is, what are all the CFTs that have higher spin symmetry? Are there others beyond the theory that Vasiliev found? So if there was another CFT, it would be dual to another bulk theory, which would be a theory beyond the one that Vasiliev found. And we'll answer this question here. So we'll answer the question of how many CFTs there are. And they're basically free field theories. We won't show a result which is as strong as this, but almost as strong as this. And this is the analog of the Coleman-Mandula theorem for CFTs, which do not have an S matrix, or if you wish, is the Coleman-Mandula theorem for ADS. In addition, we'll also constrain some aspects of theories where the higher spin symmetry is just slightly broken, so broken by 1 over n effects or broken by quantum effects from the bulk point of view. Now, why is, let me just give you further motivation. Why is higher spin symmetry interesting? Now, you might say, well, if it describes just free field theories, why do we care? It might be a complicated way of analyzing free field theories. Now, even for that, it's interesting because it captures the gauge invariant symmetries of free gauge theories. Okay, so in gauge theories, you cannot really talk about the elementary fields in a gauge invariant way. So it's convenient to think about this as the symmetries of free gauge theories. And furthermore, in many cases, the interactions is the breaking of the symmetry. So if you understand the breaking of the symmetry, you might understand theories in a new way. So in some sense, I think the most interesting aspect is the case of spontaneously broken gauge symmetries. And this we are familiar in the case of massive spin 1 fields, such as the C boson, the W bosons. And we know that, that in that case we can describe the theory through the Higgs mechanism. So we can have, even in the case that we have massive higher spin particles, if the theory is weakly coupled, we can realize that as a spontaneously broken symmetry. And so I think a challenge for us is whether we can understand spontaneously broken higher spin symmetry better, because string theory is a theory that contains massive higher spin particles, and if we could understand how this higher spin symmetry is broken in string theory, we would get a new picture of what string theory is, and we might understand it better. So this is an old idea, and not a lot of progress has been made on this idea, but the new feature, the new feature here is the fact that in ADS we really can have a situation where the higher spin symmetry is unbroken. So for example, in theories that are dual to, let's say, Young-Mills theories with a coupling like n equal to 4 super Young-Mills, you can make the coupling go to 0, and then you recover the higher spin symmetry. While in flat space, this is not easy to see how to do that. And so in flat space, the symmetry is somehow always broken, and it's hard to take a limit where it is unbroken. While in ADS, it is simpler. Now, it also is interesting to understand, in general in string theory, how strongly constraining this higher spin symmetry is. So, or how unique is string theory. So if you just say that, for example, you have a weakly coupled theory of massive higher spin particles, is that constraining enough to give you the whole structure we have in string theory, like the worldsheet and so on? That's another question one might be interested in. Now, all these are, I think, the most interesting questions. Unfortunately, they are questions that I don't know how to answer. So, but if you would like to answer how to deal with the case of spontaneously broken higher spin symmetry, you'd better understand how to deal with the case of unbroken higher spin symmetry. So we are going to go back to the unbroken case and try to constrain a theory with higher spin symmetry, assuming nothing. We don't assume a specific theory, but we only assume the existence of this symmetry and see how far we can get. So we will make some assumptions, and so we'll assume we have a conformal field theory, assuming that has all the usual properties, locality, OPE, etc. Also, we assume there is a stress tensor with a finite two-point function, etc. It's unitary and so on. Now, if our starting point is ADS, we assume that the ADS theory, whatever it is, defines a conformal field theory in the ADS boundary. Okay? And then we'll use the same properties that we use for conformal field theory. So what we are going to talk about would also constrain the ADS observables, assuming they have all the properties that CFT on the boundary has, which is well, a reasonable assumption. So this we'll also assume the theory is unitary and that we have a conserved current of spin bigger than 2. We assume there is only just a single higher spin current. We don't assume an infinite number or whatever, just one. And we make two extra technical assumptions. One is that we'll do this only for the case of a three-dimensional CFT. And the other one is that we'll have only one conserved current of spin 2. So these two presumably should be relaxed later, and we expect that the answers should be similar, except in D, should be similar certainly in D3 or bigger. And the conclusion is that we'll have an infinite number of higher spin currents with even spin appearing in the OPE of two stress tensors. So we started with one, but now we'll get an infinite number. And all the correlation functions of these currents have two possible forms. Either they are those of n free bosons in the singlet sector, and in that case they coincide with the ones you get by considering the theory we mentioned before, or they are those of n free fermions, again in the singlet sector. Now, the idea of the method is the following. First, you have to notice that we don't have the algebra of symmetries. We need to find the algebra. And this algebra is contained in the 3-point functions of the conserved currents. And we'll use conformal symmetry to constrain the 3-point functions of conserved currents up to a few constants. And then we use the existence of this higher spin charge to derive relations between the different 3-point functions. And this will determine all the 3-point functions and fix the symmetry algebra. And then we'll use this symmetry algebra to fix all the other correlators. So that's the idea of the method. So the plan for part of the rest of the talk is first, I'm going to remind you of some unitarity bounds and higher spin currents. And I'll give you a very simple argument for a very special case where you see how the higher spin currents constrain correlators. And then I'll give you an outline of the full argument. So unitarity bounds in 3 dimensions. Okay, so for a scalar operator, the dimension has to be bigger than a half. And for spin S currents, so the spin S currents are tensors with S indices. They are all symmetric and traceless. And there is the bound, the corresponding bound is that the twist should be bigger than 1. Twist is the dimension minus the spin, should be bigger than 1. And when the twist is exactly 1, we have a conserved current. So the divergence of the current with respect to one of the indices is equal to 0. Now, from these currents, we can build charges. And in all our arguments, we used only the minus indices. I mean, one of the difficulties in dealing with these conserved currents is that you have all these indices, you have to keep track of them. And we managed to do all the arguments just with the minus indices. So the index algebra is reduced to a minimum. And so we consider the minus components of all the currents. Now, if you build the charges, so the charges are a spatial integral of the 0 component of the current, or more generally, of the normal component of the current to the surface you are considering. And again, we can focus on the charges that have all minus indices. So in the rest of the talk, we are only going to be talking about these charges. We have all minus indices. And if you choose your surface to be a surface of x plus equal to a constant, you can write the charge with all minus indices in terms of the current with all minus indices. Now, one nice property of one property that is interesting about these particular charges. So this is a subset of all the conserved charges you can make out of the higher spin currents, and we'll obtain the constraint just from this small subset. And these charges have spin s minus 1, and they have twist equal to 0. Okay? So recall that the twist of the currents was equal to 1, and twist is defined in such a way that the x minus has no twist, so the integral over dy in this expression is raising the twist to 0, or it's giving a twist 0. Okay. Now I'm going to give you an argument of how you can rule out certain types of operators. And I'm just going to choose these operators because essentially they're easy to rule out, and will give you a flavor of what the argument is. So imagine you have a scalar operator which is which obeys the unitarity bound, so its dimension is bigger than a half, but let's say it's less than 1. So of course a scalar operator will have dimension much bigger than 1, but this argument will only work to rule out operators for dimensions less than 1. And so we'll also assume that we have a higher spin current of spin 4. And now when the charge acts on the scalar operator, it can only give an operator with the same twist, because the charge had twist 0, and so it can only give another operator which has the same twist. And however, if the operator it gives has spin bigger than 1, its twist is constrained to be bigger than 1, but we assume that the initial operator had twist less than 1, so this particular charge acting on the operator can only give another scalar operator. So it cannot give you tensor operators with spin different from 0. So the charge acting on this scalar can only give another scalar operator, and then matching the spins, we find that it has to have a cube derivative in the minus direction. So that somehow fixed, so this simple argument fixed how the charge was acting on the scalar operator. Of course, we assume that the coefficient is non-zero, otherwise this charge is acting trivially. And if there are many scalar fields, we can diagonalize and have this property. And then now we consider, for example, the 4-point function. Oh, I should have mentioned, so here what we've done is to constrain how the algebra is acting. Okay, I mentioned that how the algebra, this particular charge, is acting on the fields. And then we'll constrain the 4-point function. So we take the 4-point function, and this identity just implies that in Fourier space, that the sum of the cubes of the momenta is 0. In addition, we have that the sum of the momenta is 0 by momentum conservation. And these two equations imply that the momenta are equal in pairs. Okay? So the momenta are equal in pairs, and the 4-point function factorizes into a product of 2-point functions. So we fixed essentially the form of the 4-point function. And now, given this 4-point function, we can look at the operators that appear in the operator product expansion of, let's say, particles 1 and 2. And so this first term is giving us something that looks like the contribution of the identity in that operator product expansion. And these two other terms are going to give regular terms. And in particular, their dimensions are such that the stress tensor cannot appear if delta is bigger than a half. Or, in other words, the stress tensor can only appear in the right-hand side if the dimension is actually equal to a half. So we ruled out, so we have a free field, and we ruled out the existence of operators with non-trivial dimensions that between a half and 1. Okay. So that this was a very simple argument. And if you wish, you can ask, well, what is the intuition behind this? Well, you can think that the transformation is this transformation which is proportional to the cube derivative, to the derivative to the cube to the third power, is a momentum-dependent translation. And so when you have wave packets that are colliding, you are translating them by amounts which are proportional to the momenta, and so if they were colliding before, they will not be colliding later. So that's an argument you can use to argue the Coleman-Mandula theorem in flat space, and here you get it for the same reason. Okay, so that's a simple argument. Now, in the case that we have the currents have twist 1, and it's essentially the same version of the argument except a little more complicated by the fact that we have many currents that can appear here in the right-hand side. So this has twist 1, and so when Q acts on this operator, we can get a bunch of tensor operators, but they all have to have twist 1, therefore they are all conserved currents. And in principle, we can have here arbitrary coefficients, and we need to fix these coefficients. Now, some of these coefficients are non-zero because, for example, the charge acting on the spin 2 current has to give us the current generating this charge. And that has to be the case because when we integrate here over space and define the conformal generator, we know how this charge transforms under the conformal generator, and the only way we can get that to work is if this coefficient is non-zero. So the conformal algebra implies that some of the coefficients are non-zero. And that's one element we need to use. And then the second element is we need to use conformal symmetry to constrain the 3-point functions of 3 conserved currents. And this was done in these 2 papers. And they found that these 3-point functions, you might be familiar with the fact that the 3-point functions of scalar operators are uniquely determined by conformal symmetry. Now, when you have tensor operators with spin, there isn't a unique 3-point functions. There can be more, there's usually a discrete number of 3-point functions, and the number increases as you increase the spin of the operator. That's for generic operators with spin. Now, if you have conserved currents, you actually have only 3 structures, which are indicated here. So 3 structures are, one is the structure you get in a theory of free bosons. The other one is the structure you get in a theory of free fermions. And the third is a structure you do not get in a free theory. It's just some structure you can write, which is a solution of the equations. It's called odd because it involves the epsilon tensor. The invariants appearing there contain the epsilon tensor. Okay. Now, this does not imply, of course, this form of the structure of the three-point functions does not imply that the theory is a sum of free bosons plus free fermions, right? In fact, in the case of spin equal to 2, this is a result for any CFT in 3 dimensions, and certainly completely interacting CFTs will have this sum of three different structures. Now, there is a brute force method to think about this, which is you take the action of the higher spin charge, which we wrote a few transparencies ago, which was this one, and you insert that in the expression for the three-point functions. So you'll get an identity which will be derivatives acting on three-point functions and sum over various spins equal to 0, and you will get that those identities can be obeyed only if certain currents are present there, and these identities will fix all these coefficients. We know some of them are non-zero, and these equations imply that many others are non-zero. And so this leads to a large number of equations, which fixes the various terms. And these equations typically separate into 3 sets. One involves only the coefficients of the boson structure, and one for the coefficients of the fermion structures, and one for the coefficients of the odd structure. That's the typical structure of the equations. And in this way, one constrains the transformation laws, and then one can go on to constrain the correlation functions. Now, there is a more elegant method which is shorter, but conceptually, well, might be slightly confusing when you first think about it. Hopefully, it won't be. And this more elegant method tries to directly construct an operator which is defined in the following way. So you take 2 stress tensors, and you take a certain Lycon limit of Lie-like OPE limit of these 2 stress tensors. So this is done as follows. So you take 2 stress tensor at generic locations. First, you set them at the same x plus location. That's not an OPE, that's just setting them at the same x plus location. And then you take y12 to 0. There we're making the distance between the 2 go to 0. And this power of y1 extracts just the contribution from the operators that have twist exactly equal to 1. I mean, we can have some other operators with different twist, but that only selects that contribution. And that defines a certain operator which we call quasi-bilocal. In a free theory would be the product of 2 fields, but in this theory, which we don't know yet is free, it's something. This is just some operator defined in this way. And given that the higher spin current exists, we consider the correlation. We consider the action of the charge on this correlation function. We take these limits, and in this way, there is a term that we know is non-zero, and this implies there are currents with all spins essentially. So starting from some charge which can have any spin I don't know, 5 halves, for example. We get that you have all even spins appearing in the right-hand side of the OP of 2 stress tensors. And then you consider the action of these charges on, again, on the OP of the 2 stress tensors, and you can find that the action of the charges is very simple, simply given by these derivatives. And this so that fixes how the charges act on these operators, on the generators. Fixes the algebra also. And then you consider a correlation function of these quasi-bilocal operators, and you find that this charge is defined in this way. There is an infinite number of them. Fix completely these correlators and imply they are the 2-point functions of free fields. So they all factorize into 2-point functions of free fields. And the relative normalizations are fixed by the word identities of the stress tensor, which is an operator contained in this bilocal, because the stress tensor is always in the right-hand side of the OP of 2 stress tensors. And in the end, you get that it's the same as the correlators of that you would have if the bilocal was written if this quasi-bilocal was written indeed as a product of two local operators. Except that at this point we could have an analytic continuation in N. However, there is. Now, in fact, you can show that this N tilde, which is a continuous parameter, is actually an integer. And this is simpler for the free fermion theory. So in that case, there is we are guided by the fact that in the free fermion theory, there is, if we have an operator which is the square of the free fermion, then if we consider the correlation function of this operator, we would get, which is a qth power of this operator, we would get a certain polynomial, and knowing that in the free fermion theory it vanishes for some values, we know that the structure is of this form. And then if n tilde is not integer, some of these coefficients are negative, and that's in contradiction with unitarity. So that forces n tilde to be quantized. So this can be viewed as a quantization of the coupling in the corresponding Vasiliev theory. So in conclusions, we have proven, the conclusion of our statement, n is quantized, and that's the coupling constant of the Vasiliev theory. And well, there are many generalizations one could imagine. One could also consider the case of spontaneously slightly broken higher spin symmetry. And here we do essentially the same, except that we now, there are interesting theories that Chin described, which are the Chern-Simons matter theories. And in this case, the spectrum of operators is the same as in the spectrum in the free theory, or the spectrum of the single trace operators, except that the dimensions are just shifted a little bit. And there is a small violation of current conservation, and the only thing we can write down in the right-hand side is this expression. So the current can only be conserved by the product of two currents, and this is the only expression we can write down. And alpha here is an arbitrary parameter. And so if we just simply assumed we have a set of currents with, which are not conserved, but the non-conservation is constrained to be of this form, then we can insert this into correlation functions and derive a bunch of identities. So the method is the same as before. We take this, we insert it in a correlator, we integrate left and right-hand side. In the left-hand side, we can integrate by parts and get an expression which looks like the action of charges on the correlator. In the right-hand side, we insert this expression, and we use factorization to split this into a product of two correlators. And then we get a bunch of equations. And the solution of these equations, in the case of three-point functions, is that the three-point functions are given by, internally it had to be a combination of the fermion structure, the boson structure, and the odd structure, but with specific coefficients, and we find the relation between the coefficients. And at this point, we don't know the relationship between lambda and the microscopic parameters, the parameter appearing here. However, in a recent paper by these authors, they computed exactly the relation between the parameters that appeared in this solution of the word identities and the microscopic parameters. Now, as lambda tilde goes to infinity, these expressions go. When lambda tilde goes to infinity, you see this gets killed, and we get only the boson structure. And this agrees with what we expect in the Wilson-Fisher fixed point, so the large N critical theory. And in fact, we seem to have a three-dimensional version of bosonization. This is only true at the level of two-point functions, where starting from free fermions, we increase lambda, and we get correlators which are the same as the ones we get in the Wilson-Fisher fixed point, which is you get by doing an Archie flow from the free boson theory. Similarly, if we start from the free boson theory and we increase lambda, we get at least at the level of three-point functions, the correlator of the Gros-Neve model. Now, in the latest paper, they even map the parameters of the two sides. So they say bosons, if you have n bosons with a UN gauge symmetry coupled to a UN Chern-Simons level K, should be equivalent to n to fermions in that way. There are some small shifts for finite K and n. Now this is, notice that here in this three-dimensional version, free fermions would be mapped to interacting bosons, okay, not free bosons. Now there is this, this relationship is consistent with these 3-point functions, however it's inconsistent with the calculation of the free energy that was done in that paper, and at this point we don't know whether, whether this duality is perhaps wrong, or whether the calculation of the free energy has some problem. This is an open problem. So this picture is not completely solid. This is, if you wish, a conjecture. It might certainly true at the level of 3-point functions, but is subject to further verification. So in conclusions, we proved the analog of Coleman-Mandula theorem for CFTs, and we used it to constrain Vasiliev-like theories. In particular, we saw that the coupling had to be quantized. And similar methods constrain theories with a higher spin symmetry violated at order 1/n, and that's what I discussed at the end. Now, you thought I had ended, but so in the future it would be interesting to consider theories which have other single trace operators, so operators of twist 3, that can appear in the right-hand side of divergence of the current, for example, of the current of spin 4 or spin S in general. And this would be Vasiliev type theories plus some matter. And the advantage of considering this is there the higher spin symmetry can be Higgs at the classical level, so it's similar to the the ordinary Higgs mechanism. And we certainly get this structure when the boundary theory has adjoint matter. And so one question is what are the constraints on this matter? And probably the solution to this constraint is that it has to be a large n-gauge theory if the bulk theory is weakly coupled. And we would like to extend the analysis of the slightly broken higher spin symmetry case to the case when the higher spin symmetry is broken at this classical level, not the quantum level, but the classical level. And this probably will, well, at the very least, it will give us an alternative way of doing perturbation theory, but hopefully it will also help us understand will teach us how to break this higher spin symmetry in string theory. And thank you.
Thank you very much. Question?
I'm fully agree with the results of this talk, but sometimes I disagree with the interpretation of these results. So let me maybe comment a little bit. Saying that this full higher spin theory is equivalent to free theory is not in all cases true, because we know, actually, we learned from the morning talk by Xi that this only is true for two particular points in the modular space of these theories, which is infinite dimensional. But on the other hand, I would like to mention that in some sense it's just terminological, I think, interpretation, because this is about particular solutions, like saying that, well, if, say, gravity has a solution that is Minkowski, which means that curvature is zero, doesn't mean that gravity is trivial. So we can go away from the solution to find something new. So basically, I think the situation in this case is pretty much the same style, because the condition that this spin 4 current is strictly conserved means just higher global symmetry of the vacuum, in the vacuum space. So if we relax this condition, this doesn't mean that local higher spin symmetries are broken. It's pretty much like diffeomorphisms in gravity. But of course, the global symmetry they do break. And this is, in that sense, I completely agree. So from that perspective, the comment I would like to say is that those broken symmetry relations that you presented in the end of your talk, I think can be interpreted as just relations that express higher spin gauge symmetries, local symmetries on the bulk side in a non-symmetric vacuum and in some gauge. So my question is, do you agree with this interpretation?
Yeah, I agree. So the case, so the exactly preserved higher spin symmetry case corresponds to taking the Vasiliev theory and quantizing it with boundary conditions that preserve the higher spin symmetry, right? And then you prove it's a dual to a free theory. Then you have the option of putting boundary conditions that break the higher spin symmetry. That's the case of slightly broken higher spin symmetry. And then the same, basically a small variant of the method still constrains the answer. So yeah, I completely agree with this. And I think the next step would be take the Vasiliev theory, add matter, and break the symmetry classically. And that would be what should be done in the future, probably.
More questions? Comments?
Yeah, nothing.
You had this commutative diagram with the conjecture duality.
Yeah.
And you mentioned in passing that one thing did not work for
Yeah,
it. Can you elaborate on this?
Yeah, so the, in the first paper, the computation of the large N computation of the free energy was done. And well, Xi showed the computation. It had a funny behavior when lambda becomes very strong, when the theory becomes strongly coupled. And if you take the map of parameters that's suggested by the third paper, then the free energy computation in the first paper is inconsistent with the duality. Okay. But so the third paper showed some other consistency conditions on the duality, and there is this free energy computation that suggests that it is wrong. So I think it's an open problem. It's a confusing situation.
How wrong are they? Do they differ by a simple expression?
No, they are quite different. Well, there is a log lambda to the cubed power. So I think it's still an open problem whether this duality is true or is not true. Or certainly at the level of 3-point functions, it's all consistent with this idea. But yeah, we don't know. Maybe there is some, well, maybe it's just, maybe someone can figure it out. So.